Up to now, we've talked about chemical reactions in terms of what reacts and what forms. In this lesson, we're going to focus on something just as important, energy. Specifically, we're going to look at enthalpy, which is how chemists track energy changes during reactions that happen under normal lab conditions. Every chemical reaction involves energy changes, but measuring energy directly can be tricky. Enthalpy exists to give us a consistent way to keep track of energy transfer, especially in open systems like beakers, where pressure stays constant. A common misconception is that energy is stored inside substances the way mass is. In reality, energy is linked to particle arrangement and the forces between particles. When bonds break or form, energy must either be absorbed or released. This slide shows the two main types of energy change. In exothermic reactions, energy is released to the surroundings. In endothermic reactions, energy is absorbed from the surroundings. These ideas explain why some reactions feel hot and others feel cold. To talk about energy clearly, we need to define boundaries. The system is the part we're studying, usually the reaction. Everything else is the surroundings. Energy always moves across the boundary between these two. One thing that needs to be clear is the boundary between the system and the surroundings. A helpful strategy is to imagine drawing a circle around the reaction. Inside the circle is the system. Outside is the surroundings. Anytime energy moves, it crosses that boundary. Delta H represents the change in enthalpy of the system. It tells us how much energy is transferred between the system and the surroundings during a process. It doesn't tell us where energy goes, just how much moves. If delta H is negative, the system loses energy and releases it to the surroundings. That's exothermic. If delta H is positive, the system gains energy from the surroundings. That's endothermic. A negative DH does not mean the reaction is cold. It means energy leaves the system. If that energy goes into the surroundings actually get warmer. To compare reactions fairly, chemists use standard conditions. Standard enthalpy changes are measured at 25 degrees Celsius, 100 kilopascals, and with substances in their most stable states. Without standard conditions, energy values from different labs wouldn't be comparable. Using standards makes thermochemistry consistent and reliable. You will find that certain enthalpy changes are commonly used. The energy change when 1 mole of a compound forms from its elements. Another is the standard enthalpy of combustion. The energy released when 1 mole burns completely in oxygen. Enthalpy changes scale with the amount of substance reacting. If you double the amount reacting, you double the energy change. Delta H is directly proportional to the number of moles involved. When solving problems, always start by identifying the reference reaction and its delta H. Then compare the given amount to the reference amount and scale the energy change accordingly. A thermochemical equation is a comprehensive representation that incorporates both the meticulously balanced chemical equation and the precise enthalpy change, signified as delta H. This equation meticulously chronicles the shift in energy during a chemical reaction, providing critical data regarding energy consumption or production. The value of delta H, signifying the heat change associated with the reaction, strictly pertains to the represented reaction in its exact written format. Any minor modification in the reaction constituents, their physical state, proportions, or temperature, could significantly influence the delta H value. Thus, it's imperative to understand that the delta H value solely applies to the reaction precisely as it's described, allowing no room for any alterations. The coefficients in an equation represent moles, and the delta H value is tied directly to those coefficients. If the coefficients change, the dH value must change too. Should a chemical reaction undergo a reversal, the sign attached to delta H, the symbol representing the change in enthalpy or the total energy within a system, inextricably swaps over. Nevertheless, the absolute value or magnitude of delta H remains unaltered amidst this process. Consequently, energy previously liberated during the original process is subsequently absorbed upon the reaction's reversal, and the energy originally absorbed reverts to being released. An unfailing mirror image of energy transformation. Energy can be shown as a dH value, as a product, or as a reactant. All three representations describe the same energy change. They're just written differently. Breaking bonds requires energy. Forming bonds releases energy. The overall dH depends on which of these effects is larger. Enthalpy values are always relative. A more negative delta H means more energy released, but that doesn't automatically mean the reaction is better or safer. Extremely exothermic reactions can be useful, but they can also be dangerous. Understanding enthalpy helps chemists balance efficiency, safety, and practicality. Distinct chemical reaction pathways may be characterized by significantly varying levels of activation energies, with some requiring greater energy inputs to trigger reactions. Nevertheless, the comprehensive enthalpy shift for the reaction remains unaffected by this diversity in activation energy. Instead, it is solely dictated by the initial and terminal states of the reactants and products involved. Since enthalpy solely relies on the states at the outset and conclusion of a reaction, the intricate processes and varied paths the reaction takes become inconsequential. This key concept forms the robust bedrock upon which Hess's law is firmly established. At this point, you should be comfortable defining enthalpy, identifying systems and surroundings, interpreting delta H signs, and working with thermochemical equations. Look at this list. If there is anything you are not sure of, review the notes and textbook, rewatch the videos provided, or even reach out for help. Next, we'll build on this idea that enthalpy depends only on start and end points. Hess's law will allow us to calculate energy changes that can't be measured directly. In lessons to follow, we will elaborate upon this compelling theory, substantiating that the change in enthalpy relies solely on the initial and final parameters of a system. Utilizing the remarkable principles of Hess's law, we are able to accurately compute alterations in energy magnitudes that were previously beyond the confines of direct measurement.